The Q factor of a coil is given by the ratio of the inductive reactance and resistance of that coil. A coil will always have a resistance, however small. So the ratio of its inductive reactance over resistance is given by the is called the Q factor, and that's what Q factor is in brief. So it is dependent on frequency, because inductive reactance is dependent on frequency. So that's there. And the other thing I want to talk about in this small video is the energy stored in an inductor. So we know that in an inductor it doesn't allow the current to change instantaneously, current through an inductor. So it tries to hold the value of the current. So whenever there is a change of current, a work needs to be done, and that work is stored in the inductor. So if we want to calculate the energy stored in an inductor, we can say energy is, of course, P dt. So P is power, so the power is VI and dt. But we want to find in terms of the change of the current. So if we think of just of a circuit, let's say DC circuit, and there is a resistance and there is an inductance, and when the switch is closed, initially the current through the inductance at t is equal to 0, I is, or we can say like this, that I0 is 0 when t is equal to 0, and I steady state is, let's say, I, which is defined by E over R. The inductive reactance of the inductor is initially infinity. It doesn't allow any current to flow, because when it tries to maintain the previous current, which was 0 before the switch was closed. So initially it would provide an infinity reactance, but over time, when the steady state arrives, the inductive reactance becomes 0 and for DC, and the current attains the value of E over R in this particular case. So our final value of current is I, and we want to see how much energy is stored when the current changes from 0 to I. So if we go back here, we have this one VI dt, but we want our variable t, instead of t we want it to be I. So what we can do, we know that the voltage drop across the inductance is given by L times di over dt. So we will replace V by this one, we will substitute V by this one. So we will have L di over dt and I here and dt here. So what happens now, this is going away, our variable has changed to I. So this has now become L and I di, this particular one, this integration. So we can integrate it in order to get the energy stored. We can integrate it from 0 to I, and L is a constant, so we can take it out of the integration, and this is I here, 0 to I. So L, and this is becoming I square over 2 I and 0, so what it becomes is Li square. So that's the energy stored. It is the value squared of the current, the steady state current in this case. And when this is the stored energy, now if this circuit at a certain time, let's say this one is, this switch is again, so maybe we have now the circuit like this, with the switch here, and we have inductance here. So this switch has two positions. Let's say there is another resistance here, let's call it R2, and maybe this is R1, this is our E, and this is our inductance. So initially this is our switch, this is position 1 and this is position 2. So this circuit may be, when the switch was at position 1, so we had a current from 0 to E over R1 built up, Now when this switch is taken to position 2, what we have is, the situation we have is like this. So now there is no source, and this current, the inductive current which was flowing in this direction, will keep flowing in the same direction and will decay. It won't become zero instantaneously, it will decay over a time, and that for that moment the current will be flown because of the energy stored in the inductance. So that energy will be dissipated through the resistance, and the current will flow in that time. So that's what happens in inductance. So yeah, it's just a short video over on this.